that all the processes should agree on who is the leader. Right? And second point is, it generally does not matter which specific process is the leader. As long as all the processes are agreeing on a particular process being a leader. So let's say we have 10 processes, and any one of them could be the leader. Just that each of the 10 processes should agree that let's say fifth process is the leader. So all the 10 processes should agree that the fifth process is the leader. So let's quickly take a look at one algorithm for leader election. So we'll take a look at what is called as a Bully algorithm. So again, the textbook discusses multiple algorithms, and I think almost all of them are. The textbook discusses 2 algorithms, or maybe more than that, many more algorithms. So we'll just discuss one algorithm that will give us an idea of how do we elect leaders in a distributed system, and then we'll move on to Apache Zookeeper. So Bully algorithm is very simple, very straightforward. So what it says is that let's say we have n processes, right? And within these n processes, we assign a process ID to each of the processes. So Bully algorithm, at the end of Bully algorithm, what will happen is that the process with the largest PID, largest process ID, largest identifier will take over and become the leader. So it's a very simple algorithm. But let's actually understand it from a distributed system perspective. How do we actually come to this conclusion that, or how do we ensure in a group of processes that the process with the largest process identifier, the PID, becomes the leader? So let's take a look at the algorithm. So let me just briefly define what is the end result of this Bully algorithm. So the process with the largest process identifier is selected to be the leader. So before we actually dive into the algorithm, why it is not straightforward? I mean, so why do we even need to have an algorithm for that? Let's say so we have a group of processes, just 10 processes. Let's say there are n equal to let's say in an example, in a hypothetical scenario, there are 10 processes in the system. Now, can just every process conclude that PID equal to 10? Let's say the PID is a number from 1 to 10. So can we just conclude that PID equal to 10 is the leader in this group of processes?
I don't know whether PID is equal to 10 is even alive or not.
Right. So that is the problem, right? So we don't know out of these n processes which ones are alive, which ones are dead, right? So therefore we need some algorithm, although it will be very straightforward, but still we need some way to periodically also or regularly make sure that there is a leader in the system.
And so what if the PIDs are not assigned in like a sequential order? It could be assigned in some random way as well.
Right. So as long as there are some PIDs, the algorithm will make sure that the process with the largest PID wins. Okay. Yeah.
I want to be sure that the process is alive or not, and there is a list of processes that are there for the system, and we select one part, like that would be choose any.
So you can. So I understood your question. So think of it from a distributed system perspective. You have, let's say, 10 machines. Each of the processes is running on different machines. Now at t equal to 0, let's say we knew that. So the way we ensure that what processes are alive or dead, we ensure it via communication. So each of these processes interact with each other via regular message passing. So if some process, if let's say the process with the highest identifier, PID equal to 10 is not alive, then the nodes will not be able to send or receive messages from that node. So therefore, it's not obvious which node is up, which node is down. Right? So we need to continuously interact with the so each process needs to continuously or regularly interact with the other processes in the system to identify which processes are alive and which processes are not alive. Right, so just one more detail. Let's say, yeah.
So who does this bookkeeping that this process is alive or not?
So the processes themselves are keeping the book. Our processes themselves are monitoring which processes are alive in the system or not. So it's a good. So one thing is that so each process is initially given, let's say, the full set of process details. So let's say there are 10 processes in the system. So at the start, each process is given the, let's say, in a distributed system there are 10 machines and each process is running on different machines. So each process is identified by an IP address and port number. Right. So at the beginning, each process is given this entire list of IP addresses and port numbers. Now each process will itself communicate with each of these 10 processes, the other 9 processes, and keep a track of which processes are alive, which processes are not.
So is that similar to the decentralized algorithm?
Yeah, so this is, you can say, similar to, so the leader election is sort of happening in a decentralized manner, but once the leader is elected, then so there is this terminology of leader and the follower. So there is one leader and the other processes are followers. So once a leader is, so before the leader is elected, it is sort of functioning in a decentralized manner, where each machine interacts with each other, every machine interacts with each other to identify the leader. Once the leader is selected, then all the followers contact the leader for mutual exclusion or any other purposes. Does that answer your question?
Excuse me, sir.
Yeah.
So to my understanding, like, why are we electing the leader based on, let's say, like the highest PID number, and why not by the duration of which the process is gonna exist?
Right. So you can so this is like the basic algorithm. Now you can make additions on top of this. So maybe you can have one metric which you can add is, instead of just looking at the PID, we'll also look at what is the expected lifetime of this process. That will be one metric, right? Based on that you can decide. So each process will, instead of just passing the PID around, they will just pass their lifetimes. Right? And you can have other metrics also. So you can have, let's say, the reliability of the process as a metric, not just the lifetime, right? So if a more reliable process, right, or a process having a good network card, that might be a good choice for the leader, right? Because everyone is going to interact with the leader. So there can be multiple ways in which how we decide a leader, but the algorithm will still remain the same, that each process will pass messages to every other process, and then in the end we'll get like one leader. So PID is just the simplest way we can identify, but we can have other metrics also. Yeah.
So what if let's consider as you said that the process will be communicating and then electing the leader. So what if due to some XYZ reason the process is not able to communicate right? So it will be reject out that process.
So let's say there are 10 processes. Now 2 processes are not able to interact with any other process. So in that case, they won't be able to perform the required operations, right? So let's say, so as we look at Zookeeper, so Zookeeper allows like, so Zookeeper there is one leader and there are multiple followers. So it's sort of a metadata storage system in which we can read and write. So in Zookeeper, if the followers are not able to contact the leader, they can still execute the read operation from the client, but they cannot do the write operation. So they might, so if a process is not able to communicate with the other processes, it is actually disconnected from the system, right? So in that case, it may or may not function properly. So it will depend from application, it will vary from application to application. Right, so No, so from an application perspective, let's say your system has 10 processes, right? In a system, there is a system in which there are 10 processes. One is the leader, there is one leader, 9 followers. And now the outside clients, they can interact with any of the 10 processes, right? So for we'll take a look at Apache Zookeeper, and then probably this question will be answered. So obviously there is no 100% reliability here, and this problem of network partitioning, let's say is very common in distributed systems, right? So again, depending on the application, you basically make adjustments. So there is SCAP theorem, if you have heard, like consistency, availability, and partitioning. Right? So you cannot ensure all three at the same time. Only two can be ensured, right? So therefore, based on the application, you make adjustments. So CAP theorem we probably studied somewhere in the middle in this course, right? But still, yeah, of course, there is no surety of 100% reliability in Okay, so in the bully algorithm, so let's say there are n processes, right? And each process is numbered from P0 to Pk to Pn minus 1, such that ID of the kth process is k, just a simple integer or natural number. Now, so just let's say at the start, what happens is every process, so any process Pk sends the election message that it wants to conduct the election and identify the leader to all the processes with the higher IDs. So that is Pk will send to Pk plus 1 up to Pn minus 1. Why this is so? Because we already know that the process with the highest ID will be selected as the leader. So a particular process need not send this message, election message to the processes with the lower PIDs, lower IDs or smaller IDs. If no,
This algorithm assumes that everyone knows where everyone is. If I just add a new user to the system,
then you need to notify all the
Yeah.
processes. Yes. So if no one responds to Pk's request, Pk understands that it is the process with the largest ID. So Pk wins the election and becomes the coordinator. So we'll come back to shortly. So we come back to the scenario. What happens when the coordinator is selected? So something more also. So we also need to communicate to other processes that now Pk is the new coordinator. So that we'll take a look at later on. But let's say if someone responds, right? So if any process responds to Pk's request, then when this process which has responded takes over, the election, and now Pk will just sit quietly and wait for the final broadcast of who is the coordinator. Right, so we'll also take a look at the example. So eventually what will happen is, so after this third step, the new coordinator announces its victory by sending a broadcast all the processes. Right, so it will just send its PID and inform everyone that I am the new coordinator or I am the new leader. So now actually,
Sir,
Yeah.
can you explain point 4?
what?
Can you explain point 4 once more?
So, the algorithm is very simple. Just take a look at step 2 first of all. Right? So what happens first of all is any process. So at the start, let's say there is no, we just started the system, right? There is no leader, there is no coordinator. So every process will send an election message to all the processes which are having higher IDs than itself.
So a process knows which process has a higher.
Right. So at the start only all the processes are provided with the entire list of processes present in the system. Right. Then if it receives a response from any process, right? If it receives a response back, right, then it will just sit back quietly because it has received response from at least one of the processes which is having a higher PID, higher process ID. Right? So I'm just using the word PID, but it need not be the identifier. It will be just a unique identifier which can be sorted. Right? So now ultimately, so eventually what will happen is you will get a state where all the PIDs, all the smaller PIDs are just waiting, and only the largest ID process, right, has not received any response from the lower PIDs, smaller IDs. In that case, then this process with the largest identifier will send the broadcast message to all the processes saying that I am the new coordinator. So let's quickly take an example, and this will surely make things completely clear. So this is again directly taken from textbook. So this is figure 5.20. So let's say there are 7 processes in the system, right? 0, and just for time being, assume that at the beginning or at some point in between, the 7 process is not available. Right? So this is dead. And therefore we want to conduct an election. So consider a scenario where the 7th process has just died and the other processes are not able to contact the 7th process, right? Process 7, and therefore they want to conduct election. So now let's say this is identified by process 4. First of all, so process 4, let's say start sending message to 5, 6, right? It cannot send to 7 because 7 is already dead. It is not able to contact 7. Now 5 and 6, both 5 and 6 are alive. So they will send a response back to this process, right? So what will happen is, we again draw this diagram. So they will send an OK message, right? So this is an election message, request for election. Now both 5 and 6 will send messages to the higher PIDs, higher IDs. Okay, so this is A, this is B. So so 5 will send to 6, right? And six will send to 7. So actually, for now we can just assume that they are also sending to 7, although 7 is not responding. The dotted line says that no response as process 7 is dead. then what will happen? Right? So 6 will respond back to 5 that it is alive. Six will respond back to 5 that it is alive. Right, and note that 6 has not received message from any process. So therefore, now 6 will declare that it is the coordinator. So it will now broadcast this coordinator message to all the processes.
आईडी सर्च करें ना
Right, so it will send it to 5, it will send it to 1, it will send it to 2.
तो तो मैंने ऐड करा मतलब से मॉडिफाई भी तो करूँगा ना मुझे एडिट करके छोड़ना है वही छाप किसी यूट्यूब पे काम हो गया स्पेसिफिक टॉपिक में कुछ नहीं
So finally,
हमने बात छेड़ ही दिया तो
process 6 is selected as the coordinator. Okay. So this is very straightforward.
3 का 2
Any questions on this Boole algorithm?
If the process 7 becomes alive in the middle of the selection period,
Right.
and then the process has the same number.
So why will they have the same number?
Because when 5 was voting, 7 was alive, then when 6 began voting, 7
Could you speak a bit louder?
when 5 was voting, 7 was alive, and then 6 began to vote. 7 came alive again.
So let's say 7 came back again. So it will have its process ID, right? 7. So in that case, so now 7 will start the election, right? So 7 actually doesn't know if there is any leader in the system. So 7 will start the election and eventually the leadership will come back to 7. Okay?
Like how will 7 start the election because there is no higher PID.
That's true. So 7 will actually now send this coordinator message to all the processes and then everyone will change. Okay? Make sense? Nitin, you had a question?
Yeah, so sir, the order in which the election message is sent, like first 4, then 5, then 6, is it in the increasing order of the process?
No, no, no.
or is
So,
it random?
so here we have just considered a scenario where all of a sudden 4 realizes that actually it is not able to contact the leader. So any process which is not able to contact the current leader, that can start the election. So in the first figure, here, right, we might as well have process 2 start the election, process 5 start the election. So any process can start the election as soon as it comes to know that it is not able to contact the leader.
So if 7 becomes alive after the election, it's not to contact the hierarchy.
So let's say 7 comes back after the new leader has been selected. So as someone asked here that 7 doesn't have, so 7 actually cannot send any election message to anyone because all the processes are having lower IDs. So 7 will directly send the coordinator message to all the processes.
So after the election is done in 6, this multicast has been done by 6. After that, 7 becomes alive.
After that 7 comes alive, right? So now 7 should become the leader, right? The current leader is 6 and 7 should become the leader. So 7 will now send the this coordinator message to all the processes that I am the new leader.
If 7 sees that the process with the PID less than itself is the leader, then it
So like strictly sticking to this algorithm, 7 cannot see that. So the algorithm is having only 3 types of messages. One is the election message, right, which is sent, which each process sends to all the processes having higher PIDs, higher IDs. So in this case, 7 doesn't have any higher ID process, right? So it cannot send the election message. It cannot send the OK message because the leader was already elected. There is no election happening right now, right? So the only message which it can send is that I am the new coordinator because there is no one who is having the higher ID than me. right? So after 6 is elected as the leader, if 7 comes back again, it will just send the message of that I am the new coordinator now. So everyone will now shift to 7 basically. 6 will also send to 7. 6 will also shift to 7 because everyone is actually agreeing that the process with the higher ID is the leader in the system. Okay?
So it is a way to have elections in a system in which the processes do not know which all machines are there in place. Because this assumes that you know which all machines are there.
Right. So in that case, ultimately, just try to understand why do we need a leader. So we need a leader. So either we need a leader from among the set of processes we have, or we bring someone from outside, right? That is what happens in an organization, right? Either we become a leader from within the organization, or we bring someone from outside, right? So in that case, you will just have someone from outside. So if you want to ensure that, so this is a problem with this. So there is something called as so one thing which I have not discussed is, and I think book discusses it at some point, and we might also discuss it at some point, is that how do we now do this communication in a group of processes? So each process, so the flaw or the drawback of these approaches is that, or the decentralized or distributed approach is that each process needs to keep track of all the other processes. So that is a drawback. Right now, if you want to do away with this drawback, then we need to then shift to centralized approach, right? Where there is already a coordinator. Right? So yes, at the end of the day, if you need to elect a leader among yourselves, then you have to know who all are present. Yes, sir.
So why do we have to, so like in this, so when 4 sends an election message,
What?
let's say in this situation 4 sends the election message,
Right.
it gets a response from 5, 6 and 7 does not get a response. So you already have the information that 6 is the highest AID that we have.
Right.
Why can't it just broadcast that message?
But sorry, what? So you are saying? So I see your question. So question is, if let's say 4 sends a message to 5 and 6, it already. So 6 actually doesn't know, right, whether 7 exists or not.
But 4 knows that 7 does not exist.
Yes. So if 4 can send this information, then we can.
So we
then
don't
6
even need
can
to go
decide.
ahead and additional computation. So why are we even
So
going?
yeah, so that would be a variation of the algorithm. In that case, what you can say is that, so it is quite possible that by the time 4 is sending this election message, 7 comes back again. So in fact, 4 did try to send this election message 7
but
also.
if 7 comes back again, it will call an election anyway, so that is irrelevant.
No. So first scenario is that, let's say 7 doesn't come back again, right? So in that case, you are right. So in that case, if 6 is already told that 7 does not exist by 4, then you don't need to conduct further election, right? But so here we are just discussing the default algorithm, the basic algorithm, and then you can make improvements on top of that. So that would be one optimization which you can do. Okay.
So technically, I still have some doubts, but if 7 joins after the elections, then already accept that 6 is the coordinator now, and instead of starting the election. For example, if 7 and 8 do more nodes join here, what will happen? Shouldn't be the 6 that 6 is the coordinator.
So yes, actually practically speaking, that is what should happen, right? So we'll take a look at Apache Zookeeper. I think that's what happens there, right? Yeah. So now I'm able to recall. So Zookeeper, that is what is happening here. So any nodes in Zookeeper, we don't have this notion of. So we do have this notion of process IDs, but we also have this notion of which process has the most updated information of the system, or the most updated view of the data which the system is storing. So that process can become the leader. Or the other possibility is that, so even if we wanted to always ensure that the process with the highest ID is the leader, in that case now 7 actually needs to first get the latest view of the system, and then it can become the leader. Okay. So in practice, yes, what you are saying makes sense, that we should have at least one leader, right? And that need not be dependent on the process ID. Yeah.
When 7 becomes the new leader, let's say broadcast the message to
So again, we come back to the same problem of network partitioning, right? So those messages. So here we are sort of assuming that.
Some know that 7 has become the coordinator and some do not know that 7 is the coordinator.
So eventually they would come to know, right? So let's consider two scenarios, right? One is, let's say 6 has accepted that 7 is the coordinator. Then whenever some follower who has not accepted 7 as the coordinator sends some request to 6, so 6 will deny I am not the coordinator. Then that follower has to now figure out who is the new coordinator now. Right? So if, let's say, just for the sake of example, again process 4. So process 4 is, let's say, is not able to receive the broadcast message of process 7. Right? In that case, it is still contacting process 6, but process 6 is now not the new current coordinator. So in that case, 6 will inform that actually it cannot perform the coordinator function.
Sir, what if 6 itself does not receive the message from 7? Let's say 7 joins the system, it sends a broadcast. Let's say only for right now 0 and 1 receives the message.
Right.
So 2, 3, 4, 5, 6 are all contacting to 6, and 0 and 1 are contacting 7. So now what would happen?
So one assumption in this algorithm is that messages are not lost. I mean, that is the underlying assumption. So again, we are basically coming back to the same problem in a distributed system. There can be this problem of network partitioning. So the network partitioning, so you can maybe, if you're more interested, you can go and read the CAP theorem, CAP theorem. It is a very important theorem in distributed systems. So the scenario which you just explained, that there are two partitions basically. One partition is considering one node as the leader, and the other partition is considering the other node as the leader. Right? So in that case, we just have two partitions. Right? So the system has become unreliable, you can say. So if a read request, so thinking it from the perspective of a read request and a write request, right? So read request, if it happens to one partition, you will get some data. Read request, if it happens to the other partition, you will get some data. Now still the system can maintain consistency by assigning like data versioning and timestamps to each data object. Right? Still, so whatever data you get as part of the read request, you will still have a timestamp. So in that case, you can get stale information, but at the same time it won't be wrong, because that just says that you're not able to contact the servers which are having the most updated information.
But let's say some nodes send a write message to 6, and then some nodes are sending write message to 7. So
Right.
how would they know that there are some write messages which have not been updated?
So yeah, so write operation requires actually to have so write operation will require. So again, it will depend, right, how the data is stored. So does 6 even have access to the data to which it is writing, or does 7 has access to the data which it is writing? So ultimately,
Okay. Yeah.
right? So
If the
ultimately you
data
will
is
need
shared,
to have
then
one
they can
coordinator.
know.
What?
If the data is shared, then they can know that this is a common place, so they would both be writing.
Right, so if they are actually both able to access the common data shared, right? So then actually we can say that then the network partitioning problem is not there, right? So actually let's finish this algorithm and then discuss Zookeeper. So Zookeeper is a real it's a real system. So we'll discuss how actually election happens there. This is sort of a so the problems which you are raising, these problems do exist in this algorithm. So this is not a perfect algorithm, and these problems will arise when you have this network partitioning and all that. And then you will have to basically add, some more, you can say, bells and whistles to this algorithm to make sure that it gives us some result. So it might not be consistent. So we need to add some more details to the algorithm to make it work in a setting where the nodes are not able to interact with each other. So this algorithm assumes that the messages are not lost.
What is 8 का है 4 5 4 का 5
What?
This is
No. So here we are considering a scenario where 7 is not alive. Right? So So that's not necessary.
Process delta perspective. ये क्या है? Qs.
All right. So let us now. So I hope at least so whatever details the algorithm has, those are clear. So in essence, what is happening is the process with the largest ID is selected as the leader, right? And what happens in case of network messages being lost over the network, that is not covered by the algorithm. The algorithm assumes that the messages are always received by the receiver, all the receiving processes. Okay, so now let us take a look at, so the book actually has one more algorithm, related algorithm, which is called as the ring algorithm. So we are not covering it as part of this class, but if you are interested, you can take a look at this algorithm from the textbook. So as you've already seen that there is a lot of detail when it comes to mutual exclusion, leader election, and so on. So all of these simple services which need to be there as part of a distributed system for making it more useful and reliable, right? So let's say if you are building out a new application, distributed application, if you were asked to implement all of these like functionalities that the system should provide, mutual exclusion, you should write an algorithm for leader and all that. So there can be many bugs in the code which you write, right? So I mean, we can all understand from the set of questions which you people have asked. There are a lot of possibilities in a distributed system. There are endless possibilities in a distributed system, and no matter how good programmer you are, it will always be a tough job writing a good distributed system which is bug free, where there are no bugs for mutual exclusion, leader election, and so on. So therefore, so this Apache Zookeeper, the thing which we are going to discuss now. So Apache Zookeeper sort of does this job for a variety of applications. So let's say, we are building a distributed application and we require mutual exclusion over a resource. And in that case, you can just use this the API which is exposed by Apache Zookeeper, and Apache Zookeeper will take care of all the locking, unlocking, and so on. So what I will do is, in this class we don't intend to cover the full details of Apache Zookeeper. So I will briefly describe some of the use cases. I already described what are the use cases of Apache Zookeeper. Apache Zookeeper. It provides API for building a distributed application which can easily or conveniently have these functionalities of mutual exclusion, leader election, and so on. So in order to do this, I'll just give a brief overview of some of the components of Zookeeper, and then we look at, for example, how do we achieve mutual exclusion using Zookeeper, and then we'll also look at leader election in Zookeeper or using Zookeeper. So Apache Zookeeper is an open source project. Right, so it is actually used by many large scale other, so it is used by other Apache projects which are very popular, for example Apache Spark, Hadoop, and so on. At some point Kafka was also using it, but now they seem to not use it anymore. Apache Kafka started with using Apache Zookeeper, and then they eventually returned to building their own algorithms for mutual exclusion and all that. So it provides facilities for supporting these various coordination tasks. Such as locking and or also the mutual exclusion, leader election, and so on. Right, one concrete example is that in Apache Kafka, so previously Apache Kafka used to use Apache Zookeeper. So in Apache Kafka, so for a particular instance of Apache Kafka, we have multiple brokers. So there can be multiple brokers. So Apache Kafka is very similar to RabbitMQ, which we discussed in this class, and you are also working on RabbitMQ as part of your assignment. So in Apache Kafka, there can be multiple brokers in an instance in an Apache Kafka's instance, and there is a need of leader election. Which broker should be the leader? Right, so to achieve this, Apache Kafka uses Zookeeper, and to elect the leader among the set of brokers.
मतलब दोनों के अंदर सेम चीज़ होती है ना एक्सचेंज की.
Okay, so how does it provide this coordination? How does it provide these coordination services? It provides these services using. So it uses what is called as a share. So it uses a shared data structure. So by shared I mean this is actually shared with. So it exposes a data structure. So actually let me retrace this. So it exposes an in-memory data structure. For providing all of these coordination services. And what is this? How is this data structure organized? So this data structure is organized. So this data structure is organized in a tree form. Organized as a tree. Similar to what we have, so similar to a standard file system. So I'll give an example quickly to just to make this more clear. So right now what we are discussing is, so we are just discussing what is Apache Zookeeper and what components it has. So Apache Zookeeper has this tree-like or hierarchical so it uses the term hierarchical namespace. Or data structure, and this is very similar to the standard file system which we have all seen. So for example, this data structure has a root, right, which can be accessed via this /name, the root, and then this root can have multiple children, right? So for example, there is a separate namespace for application 1, and then there is a separate branch for another application, and then each of these applications has further branches, right? So this will be addressed as app 1, P1, app 1, P2, app 1, P3. So Apache Zookeeper stores this tree-like structure in its memory to provide this coordination service. How it actually uses this tree-like structure, we'll take a look at it shortly. But just for now, let's understand what is the data structure which Apache Zookeeper is using for providing these coordination services. Now each of these nodes, so each of these nodes is called as a Z node, and it has some data stored. Right? So what data is stored, it will again vary from application to application. So when an application is interacting with Zookeeper, in essence what it is doing is it is interacting with this shared data structure or in-memory data structure. So what are the operations which Apache Zookeeper allows for any client to make on this data structure? So what are the operations which Apache Zookeeper allows on this data structure? Let's take a look at that. So let's start from here. So number one, if any application wants to create a node, right? So create operation is allowed. So this creates a node. So there are two possibilities. So let me first write out the definition. So it creates a new node in the tree. But it is possible that multiple processes want to create the same node, right? So there are two possibilities. If the node already exists, this operation fails. Right? And if the node does not exist,
Sir, who are going to execute this operation? The app.
what?
Who are going to execute this operation? This create and this data structure supports these operations. That I got. Who are going to use those operations?
So Zookeeper is the central entity which is providing this coordination service. Now just imagine that you are building a distributed system or distributed application which requires some of these coordination services, or let's say it requires writing to a shared file. So there are, let's say, two processes which require writing to a shared file. So what they will do is they will just ask the Zookeeper to provide a lock over the shared file. So for accessing this lock, you have to make changes to this tree. So there are so when I say so your question is who are making changes to the tree, right?
Yes.
So there are outside clients. So think of Zookeeper as a server, and then there are multiple clients. So clients are making changes to the tree which is stored inside the Zookeeper server. Okay. And then there are other operations, for example delete. So So let me actually just write down all the operations and then I'll just briefly explain what each operation means. So delete tries to delete a node. So if the node exists, then it will be deleted successfully. If the node doesn't exist, then it will fail. Right, and then we have get operation or read operation. Right, and then we have set operation or write operation. And then there is also a functionality for getting children of a particular node, right? And then there is this operation of exists, just to check whether a particular node exists or not. So we'll take a look at shortly how do we actually use this, but for now we are just discussing what are the operations which are allowed on this data structure. So these are pretty standard operations, right? Create, update, right? Create, update. So update is done using this set or write. Reading is done using this get or read, and delete is done using delete. Create is done using create, right? And then there are several other helper functions.
So is this like juggling Google Files?
Yeah, actually, it's similar to Chubby. So now let's actually, so there are some more details which I will explain in due course of this lecture, today's lecture, but let's quickly, just to motivate the use cases of Zookeeper, let's quickly take a small example of how we can actually implement a locking service, or how can we ensure mutual exclusion using the Zookeeper. So let's take a look at Zookeeper locking protocol. So this can be used for mutual exclusion. Right. So what do we need in a locking protocol? We want functionality like for acquiring a lock, right? And then we want a functionality for releasing the lock. And if the lock is already occupied or owned by some other process, then the process should wait, right? So just for the sake of simplicity, assume that there are two processes, right? And these two processes want to acquire lock for the same resource. Now how do they identify, or how do they tell the Zookeeper that they want to access the same resource? By basically the resource will have the same name, right? So what they will do is, so how do we acquire a lock in Zookeeper first of all? So the client requests Zookeeper to create a new node in the tree. Right? So let's say it says create. So forward slash is the root. Let's say it says create forward slash lock. So essentially that is, so using this forward slash lock, we are telling Zookeeper that so this is the identifier, or this is the name for a particular resource over which we want to have a lock. Now so what Zookeeper will do is, if lock doesn't exist, Zookeeper will create this node, right? And inform client that it has acquired the lock. So actually Zookeeper will just tell that the operation is successful, and the operation being successful translates to acquiring the lock.
Over this file called log.
So this is just a So this is just the data structure inside the zookeeper's memory, right? So slash lock actually is just a signifier or an identifier for a particular resource over which we want mutual exclusion, right? So this is not the resource per se. So I mean what I'm trying to say is that this slash lock, right, this lock node is just a node in the server's memory, right? That is just used as a placeholder for identifying whether we can access a particular resource over which we want mutual exclusion. Right, so all the clients will have the same mapping from, like, so what does this lock
that's
represent?
view
It will represent a particular file, let's say,
दिया प्रॉफ को भी
right?
तो मतलब सुन
Does that make sense?
अभी मतलब नहीं आ पाएगा तो मैं था मेल क्या कर
So if let's say if the lock already exists, right? Then the operation will fail. So zookeeper will notify. So the create operation will fail, and the client will understand that some other client is actually using this resource. The client understands that some other client
शशांक ने वैसे लिखा है टिप्पणी पे ये मतलब
is using the resource. So in other words, it is not able to acquire the lock. So then what will this client do? So let's say it is not able to acquire the lock. What should this client do?
The client can spawn a new thread and basically creates a new thread so that one of them waits for the lock.
Right. So this client will now wait.
ठीक है
Right,
सबका
so-
different लिखना है
Actually, let me just name this just to. So client A requests zookeeper to create a new node in the tree, right? And inform client A that it has acquired the lock. If lock already exists, the create operation failed. Now client A understands that there is some other client. That some other client is using the resource. So client A will now wait. So there is one more detail. Which I just mentioned here. What it will do is it will actually it will subscribe
आइडियल था ना
to all the notifications related to log. So whenever let's say this log is deleted, so the zookeeper will notify the client that now this log has been released. You can move forward and acquire this log.
क्या लगाएगा
So the second operation is releasing the log. So releasing the log is also very simple.
चुका हूँ
What? No, so it will subscribe. That's what I said. So it will subscribe, right?
Okay, so now it's the responsibility of zookeeper to inform them.
Right. So now zookeeper will inform the client that so whenever any change happens to this node.
Okay.
And if there are two clients trying to access the resource, so it maintains a queue.
Right. So it will maintain.
Which process first asks for the lock?
Sorry, what?
So it will basically just maintain which process first asks for the lock and then give it the lock.
Right. So that is ensured using this. I mean, logical timestamp, etc. We discussed, right? So using the timestamp, you can identify which request came first, and that request will be
logic would be
served.
hired by a part.
What?
That whole logic would be handled by
Correct. So let's say there are multiple clients trying to create the same node. So in the order zookeeper receives the request, in that order only it will process the request.
So since the clients are subscribed to so if there are multiple clients who are requesting for this law,
only 20
how
is
is
over.
this
Thank you.
sending notification at the same time to
किसी को नहीं फर्क पड़ता है जो
No, so Zookeeper, so I don't know the implementation detail how it will send, but intuitively speaking, it will have some sort of a queue associated with each
ये
node,
बंदीबाजी करनी है
right? So it will
बोली
send
करना हफ्ते
the update messages to all the elements in the queue, all the processes in the queue. In what order it sends or does it give priority?
क्यों चोदी
It
सपोर्ट
will, I guess it will depend from, it will vary from application to application, but
Finger
intuitively it will
and
just
friends
send to
take
all the processes one by one. So releasing the lock is also very simple. Releasing the lock is analogous to delete operation, right?
पुरानी वीडियो है
Deleting the delete the node corresponding to the lock. Okay. So mutual exclusion, we just need two things, right? We need access to the lock, and then we want to release the lock. If you recall what we looked at in the right? So in the centralized algorithm, we had this coordinator or central server which was taking care of this job, right? So here it is taken care of by Zookeeper. So from an application perspective, so this is an important point to note. Like let's say if we were to, so the question can be why should we use Zookeeper? Okay? So from an application perspective, think that if we want to acquire a lock, we just send this command create lock. Right? If the lock is available, it will be given to us. If the lock is not available, then we can just say I will subscribe, and then everything else is taken care of Zookeeper. If you want to release a lock, then we just say delete the node, delete the lock, right? And then everything else is taken care of by Zookeeper. Right? Now let's say there are multiple clients accessing the same lock, everything is taken care of by Zookeeper. So we just need to call these two functions, create and delete. That's it. So that should hopefully help us appreciate at least little bit why Zookeeper is useful.
वो तो छोड़ मेरे राहुल तो लाइक भी कर चुका फॉलो करता है
So there is one more detail. So I'll talk about one more detail, which is probably not relevant to mutual exclusion, maybe the example we discussed, but it's an important detail. And then we'll take a look at leader election. So what is Zookeeper doing? So Zookeeper is essentially Zookeeper. So this is sort of end of the locking protocol. So Zookeeper is providing, you can say, atomic reads and writes over a shared over a data structure which is shared with or which is accessed by multiple processes. So ultimately, at the end of the day, it just does reads and writes on the data structure. That is what it is doing. So now let's understand how Zookeeper.
So one question.
Yeah.
Zookeeper itself would be an instance running on a separate machine, right?
Right. So I'll come to that shortly. So as of now, we have just from an application perspective, it's just one IP address and portal, right? That's what Zookeeper is. But inside, actually, it is itself a distributed system. So there is this master, slaves, or a leader and followers and all that. So we'll talk about how it manages itself also. That also there are some algorithms for that also. So how Zookeeper handles concurrency? So the locking protocol did not actually. So if you go back and see what are the operations supported by the tree. So there is this create operation, there is delete operation, and then there are these get and set also, right? Read and write. So now let's understand, if there are multiple processes which are reading and writing onto the same node, then how does Zookeeper ensure consistency of the data and so on? So we'll take a very simple example. What we'll do is we'll just consider again this Zookeeper system, which is from an application perspective, it's just a single server. And then there is, let's say, a client 1, and then there is this client 2, right? So what we'll look at is we look at two operations. A read operation and a write operation. So when we denote the write operation, we add three components. So there is this N, K, and A. Right. So here N is the node name. Right. So in the last example it was forward slash lock. K is the current version of the node. Current version of the data stored in the node. So as I just mentioned, Zookeeper allows us concurrent reads and writes. So it does so by maintaining this version, right, of the data which is stored in any node. So you can think of version as the, you can relate to this version with the logical timestamps which we discussed last class, right? So logical timestamps, essentially they were capturing the version of the data, or to be more precise, actually vector clocks capture that. Logical clocks also capture that to some degree. But you can relate to this version with logical clocks and logical timestamps and vector timestamps. And then this A is just the value to be written to the node. And then similarly read can be referred to as, let's say I want to read node N and then a particular version of the node. Right? And then it will fetch me this value A. So let's quickly take an example. So let's say client 1, what it does is, it let's say create operation has already happened, right? So let me just signify create. So there is a resource. So there is a node in the Zookeeper, which is denoted by, let's say, node N, and the version is 1, let's say. Right? So at the beginning, let's say C1 says I want to read this N, right? So it makes a call, read of N. It doesn't know the version right now, right? Because it doesn't have any information. So when it reads, Zookeeper gives it. So what it will give? It will basically, sorry, just a second. So when it sends this read command to Zookeeper, it will return the value, which is, let's say, N, and the version which is 1, and the value is, let's say, A. Right? Now let's say it wants to write. At some point it also wants to write, update this value. So what will happen is it will say WN1 is the current version which I have, and then update it to B, let's say. Right, so it will send this write command to Zookeeper, and then it will succeed, and then it will get read. So it will get the updated value, and that would be N, 2, right? And that is essentially B. Now let's say there is a third client, there is a second client which also does read at this point. So this also fires a read command, and then in return it gets this R and to B. Right? Now this client 2 wants to write something, update this node in Zookeeper. So it sends this update operation and it says w n2, and then let's say it wants to update it to c, right? And then it reads. Now the version is 3 and the value is c, right? Now consider this point here. After this update has already happened to the node n. So client 1 doesn't actually know that there has been an update made by client 2, right? So client 1, what it does is it has this basically version 2 with it. So what it will do is, let's say it requests let me just write here. It says wn2 and it says I want to update it to d. I want to update the second version of this node to a new value which is equal to d. So when Zookeeper receives it, it compares this version which the client has sent with the current version it has, and it sees that the client has an older version. So this operation will now fail. So this will now fail. So what should the client do? So once the client figures out that the operation has failed, what it will do is it will now refetch. It will read the updated value of node. Right, so this is how it sort of keep tracks of the multiple or concurrent reads and writes by multiple clients.
So it's like a compare and swap, but on distributed system.
Yes. Right. So each client, so Zookeeper maintains the current version of the state of the node, and the clients also maintain. And whenever they are communicating, they share their current versions, and based on that they decide whether. So based on that, the Zookeeper decides whether the client is having the most updated state or not, and then only it allows the other clients to update it. So now last point is I want to cover. I'll just take 5-7 minutes and hopefully we should be done. So till now what we have looked at is Zookeeper. We have just looked at Zookeeper as a black box or what functionalities it can provide. So in reality what happens is Zookeeper has what we already discussed. It has a leader or coordinator node. And then there are follower nodes. So how Zookeeper is implemented? It is in itself a distributed system, right? It is itself a distributed system having multiple nodes, where there is a leader node and then there is a follower, and so there is one leader node at a time, and then there are multiple follower nodes. So the leader can serve both reads and writes, but the followers they can serve only reads, right? So any client can contact any node in the Zookeeper system. If the client contacts a follower for a write, follower will just forward the request to the coordinator.
And there is just a single coordinator.
Yes, there is a single coordinator. So if a client sends a write request to the follower forwards the write request.
डायरेक्शन स्क्रैच है
To the
हर एंगल
so the follower forwards the write request to the leader. So note that writes are always performed by the leader, and reads can be performed by any of the followers. So multiple writes, concurrent writes are supported. So at a time multiple processes can read the same node, but only one process can write, because eventually all the writes will come to the leader, and leader will now order the writes in the order in which it has received the request. So then the question is, what we discussed at the beginning of the class, how do we do leader election and zookeeper? So, I don't have a lot of time. So what I'll do is, I'll just directly take you to the code which is actually there in the textbook. So at a high level, the idea is similar to the bully algorithm. Yeah.
So sir, client only contacts the followers, or they can contact the leader as well, in general.
So client can contact any client can contact the leader, it can contact the leader, it can contact the follower also. So if the client contacts the leader for a read operation or a write operation, leader will process it immediately. If the client contacts the follower, then the read request will be processed immediately, but the write request, they will be forwarded to the leader. Okay. So let's actually, I don't have sufficient time, so let's actually stop here, and then I'll probably make a video, upload it on Classroom, or we will discuss